Welcome to the Deep Dive. We're here to unpack complex tech topics and really pull out the key insights for you. Today, we're digging into something pretty critical for anyone running serious applications in the cloud, a very comprehensive, very mature AWS ECS Fargate architecture. This is designed for, well, demanding enterprise use cases.
Yeah, and our source material here, it's this incredibly detailed architectural document. What's really interesting is that it's not just theory, it's actually fully implemented, and get this, with both Terraform and CloudFormation. So our mission today, let's cut through the complexity, understand that the core pieces, how they all fit together, and really figure out what makes this setup so robust for those big mission-critical environments. We want you to walk away with a solid picture of what modern enterprise-grade cloud infrastructure really looks like. Okay, so to kick things off, let's talk about the foundation. Infrastructure as code, or IAC. What exactly are we building with here? And maybe more importantly, why implement something like this in both Terraform and CloudFormation? Seems like a significant decision.
That's a really good starting point. And yeah, it does highlight the, let's say, deliberate design here. Having it in both IAC tools isn't just about showing off. It offers genuine flexibility and taps into the unique strengths each tool brings to the table. So, infrastructure as code, IAC. Fundamentally, it just means you're managing your cloud stuff, servers, networks, databases, using code, using definition files instead of clicking around in a console.
Right, consistency, repeatability,
Yeah,
all that good stuff.
exactly. Speed, version control. It brings software development practices to your infrastructure. Now, about the two tools, Terraform, that's HashiCorp's baby, uses its own language, HCL. CloudFormation is AWS's native tool using YAML or JSON. A key difference often boils down to state management. Terraform gives you explicit control. You typically store its state file, maybe in S3 with DynamoDB for locking. Great if you're multi-cloud or have complex team structures. CloudFormation. Its state is managed entirely by AWS behind the scenes. Simpler if you're purely an AWS shop, maybe less setup. Then there's modularity. Terraform has these really powerful reusable modules. Think of them like functions for infrastructure. CloudFormation uses nested stacks to achieve something similar, breaking down big templates.
Gotcha.
But here's a big one, especially for enterprises. CloudFormation offers automatic rollback. If a deployment goes wrong, poof, it automatically tries to revert to the last known good state. That's a massive safety net.
Yeah, that's huge for critical systems.
It really is. Terraform's rollback tends to require more manual steps, a bit more intervention. Also, validation timing differs slightly. Terraform often validates more at runtime. CloudFormation can catch certain things earlier during the deployment validation step itself.
Yep.
So having both implementations available, it shows this architecture understands different enterprise needs. Maybe one team prefers Terraform's ecosystem, another needs CloudFormation's tight AWS integration and rollback. It gives you options.
That makes a lot of sense. It's not just picking one tool, but strategically using the best features, maybe even having that redundancy. It really underlines that focus on stability and adaptability. Okay, so you've got this solid IAC foundation. The next big hurdle, always, is security,
Yeah.
especially for enterprise data. How does this architecture tackle that? How does it build that fortress?
Right. Security is absolutely job zero here, and this architecture takes a very layered, very deliberate approach. It's all about isolation and restricting access based on need to know, kind of like a zero trust mindset. We basically see four distinct layers.
4 layers, okay.
Yep. Starting from the outside in, layer one is the public subnets. Think of this as your front door, the perimeter. It's designed for internet access, handling incoming traffic. Key players here, the application load balancer, the ALB, distributing HTTPS requests. Then you've got CloudFront, AWS's CDN, acting as a global shield, often paired with the Web Application Firewall, WAF, to block common web attacks right at the edge.
Okay, standard edge protection.
Exactly. Plus, you'll have NAT gateways, so your private resources can initiate outbound connections to the internet if needed, and VPC endpoints for optimized private connections to other AWS services, which helps with security and cost.
Right, keeping traffic off the public internet where possible.
Precisely. And crucially, the security groups here, super strict. Only ports 80 and 443 are typically open from the internet, tightening that entry point.
Makes sense. So layer 2.
Layer 2, private front-end subnets. Moving inside, this is where your actual user-facing applications run and also where some of your DevOps tooling might live. Your front-end containers, they run on ECS Fargate, that's AWS's serverless container engine, no servers for you to manage. Your Docker images are stored securely in ECR, the Elastic Container Registry. If your apps need shared storage, EFS, Elastic File System, is there. And of course, CloudWatch for all your monitoring and logging needs. On the DevOps side, this layer might host code commit, AWS's managed Git, code build for build and test automation, maybe even a Jenkins server if that's your CI/CD tool of choice. Security groups here control traffic flow between the front end and other internal services, like the ALB.
Okay, so the apps and the tools supporting them are separated from direct internet access, talking only through controlled points.
Exactly. Now, layer 3, private backend subnets. This is the inner sanctum, highly isolated. This is where your databases, your caching layers, maybe some sensitive serverless functions reside. Here you might find more ECS Fargate tasks running backend microservices. You'd have RDS MySQL for your relational data, maybe Elasticache using Redis for fast caching, or DocumentMDB if you need a managed MongoDB-compatible database. Lambda functions could live here too, doing things like processing events or sending notifications. And service discovery helps these backend services find each other automatically using DNS.
And the key here is the isolation, right?
Absolutely critical. Access to this layer is extremely restricted. Generally, only the ECS front-end services from Layer 2 are allowed to talk to the back-end services, enforced by tightly configured security groups. Your databases, your caches, they have no direct path to or from the internet. That massively reduces the attack surface.
Wow, okay, that's serious lockdown. The fourth layer.
Layer 4 isn't a subnet, it's more pervasive. It's centralized security and encryption using AWS KMS. This cuts across everything. It leverages AWS Key Management Service, specifically the enterprise tier in this architecture, with a whole suite of specialized encryption keys. The doc mentions 50.
50 keys, wow.
Yeah, dedicated keys for different services and data types. This ensures everything is encrypted, data in transit, data at rest. It centralizes how you manage secrets securely, which is crucial for compliance audits like SOC2, PCI, AFPA, GDPR. You get full audit trails, automatic key rotation, the works. So that deep back-end isolation combined with comprehensive KMS encryption, that's the core of the security posture, secure, performant communication flow.
That is genuinely defense in depth. It's not just one wall, it's multiple tightly controlled zones with encryption woven throughout. Really makes sensitive data hard to reach.
Okay, but what about the applications running on this? How does it handle different app sizes and needs, from tiny test apps to huge enterprise monsters? Good question. And this architecture handles that variation really elegantly, using something called task definition templates for ECS Fargate. Think of these as predefined optimized resource profiles.
Like t-shirt sizes for containers.
Kind of, yeah, but optimized. It removes the guesswork and ensures consistency. So instead of every team figuring out CPU and memory from scratch, you have these starting points. The architecture outlines specific profiles. Micro, like 256 CPU units, half a gig of RAM, 512 millib, and a 256 meter heap size. The doc explicitly mentions optimizing the Java heap, which is smart for Java shops. This is great for dev tests or tiny utilities.
Okay.
Small. Bumps up to 512 CPU, 1 GB RAM, 512 meter heap. Good for lighter workloads, maybe initial staging. Medium. 1 on 24 CPU, so 1 virtual CPU. 2 GB RAM, 2024 meter heap. Your standard workload profile, large. 2048 CPU, 2 vCPUs. 4 GB RAM, 2046 meter heap for heavier lifting. X large, the big one. 4096 CPU, 4 vCPUs. 8 GB RAM, 4096 meter heap. Clearly marked for those demanding enterprise workloads. And importantly, there's always a custom option, because sometimes you just have unique needs that don't fit a template.
That's really practical. It's not just about standardizing, it's about pre-optimizing. Teams aren't wasting time tuning basic resource allocation for every single service. They grab a template, maybe tweak the heap if needed, and go. That must save a ton of time and prevent so many performance issues down the line. This is a real boost to engineering efficiency. All right, so we've got the secure IC foundation, we've got optimized ways to run apps, but what about the day-to-day? Running the show. How does this architecture handle things like smooth deployments, knowing what's going on, keeping costs under control?
Yeah, that's crucial, right? An architecture isn't just about the build, it's about the run. And this one integrates operations really tightly. Let's break it down. First, DevOps integration. It assumes a full CI/CD pipeline, using code commit for Git, code build for automated builds and tests, and feeding into deployments managed by the IAC tools, Terraform, or CloudFormation.
Okay, the whole automated flow.
Exactly. It also mentions Jenkins as an alternative, if teams prefer that, and using Lambda functions for things like automated notifications, maybe pinging Slack when a build fails or a deployment succeeds. The goal is full automation from code check-in to running service, faster releases, fewer manual errors.
Makes sense. What about visibility, monitoring?
Comprehensive monitoring and observability. It relies heavily on AWS CloudWatch. That means structured logs, standard metrics out of the box like CPU, memory, network I/O, custom dashboards built in CloudWatch 2, plus setting up critical alarms for key thresholds. And it specifically calls out using CloudWatch Container Insights for deep-level monitoring inside your ECS Fargate containers.
Container Insights is really useful for ECS.
It is. And to take it further, this architecture integrates with Grafana, so you can build even more sophisticated dashboards, pulling data from CloudWatch and potentially other sources, visualizing things like DevOps pipeline status, the overall ECS Fargate cluster health, and importantly, infrastructure costs. Gives you that single pane of glass.
Okay, visibility covered. What about the money? Cost control.
Big focus on cost optimization. This isn't an afterthought here. Several strategies are built in or recommended. Using VPC endpoints, like we mentioned, helps cut down NAT gateway data transfer costs, which can sneak up on you. It explicitly mentions the option to use Spot instances for ECS Fargate tasks. If your workload can handle interruptions, Spot can save you, up to 90% sometimes.
Huge savings, if applicable.
Definitely. Also standard stuff like suggesting reserved instances for predictable workloads like RDS databases and Elasticache nodes, and it includes practical things like automated start-stop scripts for non-production environments, turn stuff off overnight or on weekends.
Smart, simple, but effective.
And finally, setting up AWS budgets with alerts, so you get notified before you accidentally blow past your expected spending. It's about proactive financial governance.
It really does feel like a complete operational ecosystem, not just deploying code, but managing the whole lifecycle, efficient delivery, deep visibility, and active cost management. That gives engineering teams the clarity and control they need. So, with all this capability, how does it scale down or up for different environments? Dev versus staging versus production. And where does an architecture like this go next? What are the future steps?
That's a key aspect of enterprise design, tailoring the environment to its purpose. This architecture does that very clearly. For development, the focus is on speed and low cost. It uses that small task profile, 512 CPU, 1 GB RAM, maybe scales between just 1 or 2 instances. The CI/CD pipeline trigger is usually automatic push code it deploys. Monitoring is basic, and the cost budget is tight, maybe around $50 a month, keeping experimentation cheap.
Right, lean and mean for dev.
Then staging. This is your pre-production proving ground. It steps up to the medium profile, 124 CPU, 2 GB RAM, maybe scales between 2 and 4 instances for more realistic load testing. Pipeline trigger might still be automatic, but you'd have complete monitoring enabled here to catch issues before they hit prod. The budget reflects this, maybe around $200 a month.
Okay, more robust testing.
And finally, production. This is the real deal. It uses the powerful X-Large profile 4096 CPU, 8 GB RAM, configured to auto-scale significantly, say between 3 and 10 instances, maybe more, for high availability and handling peak loads. Critically, the pipeline trigger here is often manual. You need that human sign-off, that final gate before changing the live system. Monitoring is enterprise-grade, all bells and whistles, and the budget reflects the scale, maybe $1,000 a month or more, depending on usage.
So a very deliberate ramp up in resources, control, and cost across environments.
Exactly. It aligns resources and process rigor with the criticality of the environment. And looking ahead, the source document actually outlines clear next steps, which really shows its maturity. Things like implementing multi-region replication for higher availability and disaster recovery, automating DR strategies, integrating with AWS Security Hub for a centralized view of security posture and compliance checks, building more advanced cost optimization dashboards. On the tech side, adopting AWS App Mesh for a service mesh to better manage microservice communication, adding OpenTelemetry or Jaeger for distributed tracing, getting deeper observability, and even moving towards GitOps using tools like Argo CD for managing deployments declaratively from Git.
Wow, okay, so it's not static. It's designed with a clear evolutionary path, anticipating future needs around resilience, security, observability, and deployment practices. That's really forward thinking. So to wrap up, we've really gone deep today into what makes up a comprehensive, genuinely mature, enterprise-grade AWS ECS Fargate architecture.
Yeah, we really have. We've seen how it layers security through isolation and pervasive encryption, how it builds in scalability and high availability, how it tackles cost optimization proactively, and how it integrates tightly with DevOps for smooth operations. It's quite the blueprint. And this brings up an interesting point for you, the listener. This architecture documentation mentions specific key performance indicators, KPIs it aims for. Things like achieving greater than 99.9% availability, keeping response times under 200 milliseconds, enabling more than 10 deployments per day, and keeping the cost per request under 0.0011 DOS. Impressive goals. So the question for you is, if you were adopting an architecture like this one for your own application, your own business needs, which single one of those KPIs, availability, response time, deployment frequency, or cost per request, would you prioritize above all the others? And why would